Welcome to another episode of Terry's Notes, and this is part 2 of an earlier video we did on chemical energetics. This video focuses on the calculations required for chemical energetics. So the first thing we need to look at is what is called the heat of neutralization. The heat of neutralization is the energy change per mole of water formed during the neutralization of an acid and a base. Now, if we have a chemical reaction, for example, let's say sodium hydroxide plus hydrochloric acid, and we get a salt, which is sodium chloride plus water. Now, the chemical reaction taking place in this case here, we can write it as H plus. Look at this here. We have H plus OH minus producing H2O. Alright? And the enthalpy change for this reaction is minus 57 kilojoule per mole. And this reaction is exothermic because the enthalpy change has a negative in front of it. It's minus 57 kilojoule per mole. Alright, so we can use any of these two equations here to represent the heat of neutralization of a strong acid and a strong alkali. We notice that 1 mole of water is being produced, so you need to be able to give that definition for the heat of neutralization. Now let us look at a worked example. In this example, we have 25 cm cube of a 2 mole per dm cube sodium hydroxide, and we have 50 cm cube of a 1 mole per dm cube hydrochloric acid. And both these solutions are at 30 degrees Celsius, and they are mixed together in a styrofoam cup. On mixing, the temperature rises to 38.9 degrees Celsius. Now remember, we said that the heat of neutralization is an exothermic reaction, and you would recall that in an exothermic reaction, energy is released to the surroundings. So that is why we have an increase in temperature. Initially we were at 30 degrees and now we are at 38.9 degrees. So in this question, what we need to do is to find out the number of moles of sodium hydroxide we have, find out the number of moles of hydrochloric acid we have, and from that we can calculate the heat of neutralization. So there are certain things or certain assumptions that we make. The specific heat capacity of water is taken as 4.2 joules per gram per degree Celsius. What this simply means is that we require 4.2 joules to raise the temperature of 1 gram of water by 1 degree Celsius. And we will assume that the density of the solution is 1 gram per cm cube. Now, in the case of the information given, the first thing we need to do is to find the temperature change for the reaction mixture. The final temperature was 38.9 degrees Celsius, and the initial temperature was 30 degrees Celsius. So therefore the temperature change is simply 38.9 minus 30 degrees, and we get 8.9 degrees Celsius. Now pay attention to the steps. First thing we do is find the temperature change. The next thing we need to do is to find the energy released in the reaction. And you need to familiarize yourself with this formula, and that is energy is equal to M multiplied by C multiplied by delta T. So M is the mass or the total mass of the solution after you have mixed it. C is the specific heat capacity of the solution, which we said earlier we will assume to be 4.2 joule per gram per degree Celsius. And delta T is simply the change in temperature of the reaction mixture. So we had 25 cm cube of sodium hydroxide, and we had 50 cm cube of hydrochloric acid. Therefore, the total volume will be 25 plus 50. All right, so that's where I got the 25 plus 50. The 4.2 will be given to you in the question. That is the specific heat capacity of the solution. And the temperature change is what we just calculated as 8.9 degrees Celsius. So we simply use our calculator to work this out, and we get 2,804 joules. All right, now this information is important. Now the next step, we need to write an equation for this reaction. So we have sodium hydroxide plus hydrochloric acid produces sodium chloride and water. Now, what we have to do is take the information given to determine how much moles of sodium hydroxide we have in the mixture and how much moles of hydrochloric acid we have in the mixture. The reason for this is to determine how many moles of water we are dealing with. So we start with the sodium hydroxide. The concentration of the sodium hydroxide was 2 mole per dm cube, and we use 25 cm cube. So we write up our statement exactly as I have it here. You do not need to remember any formula. So the concentration was 2 mole per dm cube for the sodium hydroxide. What this means is that in 1000 cm cube we have 2 moles of sodium hydroxide. So that is what we write. 1000 cm cube contains 2 moles of sodium hydroxide. Therefore, 25 cm cube will contain 25 multiplied by 2 divided by 1000. Right? And that gives us 0.05 moles of sodium hydroxide. The next thing we need to do is to look at the hydrochloric acid. Excuse me. So the concentration of the hydrochloric acid was 1 mole per dm cube. And what this means is that in 1000 cm cube we have 1 mole of hydrochloric acid. So we write up our statement as 1000 cm cube contains 1 mole of hydrochloric acid. Therefore, 50 cm cube contains 50 multiplied by 1 divided by 1000. So we get 0.05 moles of hydrochloric acid. Now, if we look at the equation, just by looking at the equation, we can say 1 mole of sodium hydroxide produces 1 mole of water. We can also say that 1 mole of hydrochloric acid produces 1 mole of water. Now, in this case here, we have 0.05 moles of sodium hydroxide and 0.05 moles of hydrochloric acid. Therefore, when we mix those two, we will end up with 0.05 moles of water. Now, remember the definition for heat of neutralization. It is the enthalpy change when 1 mole of water is produced when an acid reacts with an alkaline to neutralize. So 0.05 moles of water produces 2804 joules of energy. Remember, the 2804 was calculated by using E equal mc delta theta. So therefore we need to find for 1 mole of water. So we write up our statement as 1 mole of water produces 1 multiplied by 2804 divided by 0.05, and we end up with 56.1 kilojoules. Alright, the actual value is 56,080 joules. We should convert it to kilojoules by simply divided by 1000. Alright, and that's how we end up with 56.1. Now remember, we said that this reaction is exothermic, so we are not done as yet. So we say the heat of neutralization is minus 56.1 kilojoule per mole. Now, we have something called a thermometric titration. essentially we can follow the course of titration by measuring the temperature of the reaction mixture as we keep adding different volumes of the acid. Alright, so the endpoint of a titration can be determined by measuring temperature changes. So a fixed volume of the alkali is placed in a styrofoam cup. You'll notice that in all these thermometric or all these type of experiments, we use a styrofoam cup. Essentially, we are trying to limit the amount of energy being lost to the surroundings and trying to limit energy being absorbed from the surroundings. So that is why we use a styrofoam cup. So the first thing we do is put a fixed volume of the alkali in a styrofoam cup and a fixed volume of acid, let's say 5 cm cube, is added, and the temperature of the mixture is recorded using a thermometer. The process is repeated by adding more acid and recording the temperature changes. So essentially the experiment looks like this. You have a burette with your acid, and we have the fixed volume of the alkali, and we continue adding 5 cm cube volume. We stir the reaction mixture and record the temperature. So what will happen is that we will get a series of results indicating volume of acid added and temperature, and when we plot the data, we will end up with a graph something like this. So on the x-axis we have to plot volume of acid in cm cube, and so we have volume of acid in cm cube, and then on the vertical axis or the y-axis we have our temperature. So what we will eventually get is a graph which looks like this. It will initially begin to increase, it will reach a maximum and then start to decrease. The maximum point on the curve, if we drop a vertical at the maximum point, this will represent your neutralization point, and we can also determine the overall temperature change for the reaction by measuring the difference between the highest temperature change and our initial temperature change. Now the next thing we need to look at is heat of solution, and heat of solution is simply the energy change that occurs when 1 mole of a solute dissolves in water to produce an infinitely dilute solution. So in this case we are dealing with 1 mole of a solute, and when we say infinitely dilute solution, it means that no further change will occur. Okay, let us look at this worked example. So in this example we have 12 grams of potassium nitrate being dissolved in 100 cm cube of water, which is initially at 29 degrees Celsius. The temperature of the water falls to 19.4 degrees Celsius. Calculate the heat of solution for potassium nitrate. Now we will notice that the temperature of the water falls. Right now it falls to 19.4 degrees Celsius, and our initial temperature was 29 degrees. Now this means that the reaction mixture, it got cold. Therefore energy was absorbed from the surroundings. And again we will use the same assumptions we used before. The specific heat capacity of water is taken to be 4.2 joule per gram per degree Celsius, and the density of the solution is taken as 1 gram per cm cube. Now the first thing we need to do is to find the molar mass of potassium nitrate, and basically we get this information from the periodic table. Potassium, the mass number is 39, nitrogen, the mass number is 14, and oxygen, the mass number is 16. So therefore KNO3, which is potassium nitrate, will be 39 plus 14 plus, in brackets, 3 multiplied by 16, and we will get 101. Alright, what this means is that 1 mole of potassium nitrate has a mass of 101 grams. So we write up our statements to determine the amount of moles of potassium nitrate we are dealing with. So 101 grams of potassium nitrate contains 1 mole. Therefore, we say 12 grams of potassium nitrate will contain 12 multiplied by 1 divided by 101, and we end up with 0.1188 moles. Alright, now remember I said don't try to learn off any formula, just look at how these statements are written. We are trying to find the number of moles of potassium nitrate. So in our original statement here, we wrote 101 gram of potassium nitrate contains 1 mole, right? And then essentially what we are doing is cross multiplying. 12 so we take in what we have here multiplied by 1 and we divide it by 101. As in the example before, we need to find the temperature change. So it'll be 29 minus 19.4 and we end up with 9.6 degrees Celsius. Now the energy loss by the solution is equal to mc delta T, and the mass, let's just go back a sec here. We had 100 cm cube of water, so the mass of water is 100 grams, right? And the specific heat capacity of the water is 4.2 and the temperature change is 9.6. We multiply that using our calculator and we get 4032 joules. Now, next thing we have here is we need to determine the energy change for 1 mole. So we worked out that energy change of 4032 represents an energy change associated with 0.118 moles of potassium nitrate, but we need to find for 1 mole. So we write up our statement. 0.1188 moles of potassium nitrate is associated with an energy change of 4032 joules. Therefore, 1 mole of potassium nitrate is associated with an energy change of, again we cross multiply, 1 multiplied by 4032 divided by 0.1188. We end up with 33,939 joules. We convert that to kilojoules by dividing by 1000, so we get 33.9 kilojoules. Alright, now we're not finished as yet. Now we said that the reaction was endothermic because the reaction mixture absorbed energy from the surroundings. There was a temperature drop, and for an endothermic reaction we need to put a positive sign in front of our answer. So the heat of solution for potassium nitrate is positive 33.9 kilojoule per mole.